Welcome to Dr. Carminati's channel, everyone. Today, we embark on a profound exploration into the very architecture of artificial intelligence itself, specifically, how we empower these burgeoning digital intelligences to navigate and interact with the complex, often chaotic external world. We delve into a crucial framework, a foundational principle that promises to redefine the boundaries of what AI can achieve. You find yourself at the precipice of an era defined by intelligent systems, a time when artificial intelligences, once confined to mere conversation, now yearn for agency, for the capacity to do things in the real world. This isn't merely about chatbots, it's about building intelligent entities capable of meaningful action, entities that can genuinely extend human capability and resolve profound challenges. However, a significant hurdle obstructs this path: the intricate, often fragmented nature of external systems, databases, APIs, and local file systems. How do we provide AI with a standardized, secure, and comprehensible means to engage with this external reality? How do we impose order on this potential chaos? The answer, my friends, lies in understanding and implementing the Model Context Protocol, also known as MCP. What exactly is the Model Context Protocol? The Model Context Protocol establishes itself as an open-source standard for connecting AI applications to external systems. Think of it less as a piece of software and more as a universal translator, a crucial intermediary. The sources articulate a perfect analogy. MCP functions much like a USB-C port for AI applications. Just as a USB-C port standardizes connections for diverse electronic devices, MCP standardizes the connection of AI applications to a myriad of external systems. This standardization is not a mere convenience. It is an absolute necessity for scalable, secure, and genuinely intelligent AI integration. To truly grasp its essence, we must dissect its fundamental architecture. MCP operates on a client-server model. This is a familiar paradigm in computing, but here, it possesses distinct characteristics tailored to AI's unique requirements. At the heart of this architecture, you will find three key participants: the MCP host. This represents the core AI application itself, the intelligent entity you interact with, perhaps something analogous to Claude Code or Claude Desktop. It acts as the coordinator, managing one or more MCP clients. The host establishes connections to servers by creating individual clients. The MCP server. This is the program providing context to MCP clients. Critically, MCP servers possess the flexibility to run either locally on the same machine, such as a file system server launched by Claude Desktop using STDIO transport, or remotely, like the official Sentinel MCP server utilizing streamable HTTP transport. The server's location does not alter its fundamental role in serving context data. The MCP client. This is a specific component, instantiated by the host application that maintains a dedicated one-to-one connection with a particular MCP server. Its primary function involves obtaining contextual information from its server for the host to utilize. A client represents the direct channel of communication with a single server. Now consider the operational layers of this protocol. MCP deliberately divides its functionality into two distinct layers, ensuring modularity and clarity. The data layer. This represents the inner sanctum of MCP, defining the very language of communication. It implements a JSON RPC 2.0 based exchange protocol, outlining message structure and semantics. This layer encompasses crucial elements like lifecycle management, handling connection initialization, capability negotiation and termination, server features, tools, resources, prompts, client features, sampling, elicitation, logging, and utility features, notifications and progress tracking. Developers, particularly, will find this layer, with its defined primitives, profoundly useful, as it dictates how servers share context with clients. 2. The transport layer. This is the outer shell, concerned with the physical or logical conduits of communication. It manages communication channels, authentication, connection establishment, message framing, and secure data exchange. MCP currently supports two primary transport mechanisms: standard input, output, STDIO, transport for direct process communication between local processes, offering optimal performance without network overhead, and streamable HTTP transport for remote server communication, supporting standard HTTP authentication methods. The brilliance here lies in the transport layer's ability to abstract away communication specifics, allowing the same JSON RPC 2.0 message format across all transport types. Crucially, MCP maintains a precise scope. It focuses solely on the protocol for context exchange. It does not attempt to dictate how AI applications should use large language models, LLMs, or how they should manage the context that MCP provides. This delineation highlights MCP's role as an enabler, not a dictator, preserving flexibility for AI developers. Finally, in this evolving digital landscape, versioning matters. MCP employs a clear string-based version identifier following the format YYYMMDD. This date indicates the last instance of backward incompatible changes. Significantly, backward compatible updates do not increment this version, ensuring continuous improvement while preserving interoperability. Version negotiation occurs during the initialization phase, where clients and servers must agree on a single compatible version for the session. Without this agreement, connections will gracefully terminate. The current protocol version, for your reference, stands at 2025-0618. For what purpose do we employ MCP? The fundamental purpose of MCP is to extend AI applications capabilities by providing secure, controlled access to external resources and tools. It bridges the chasm between the intelligent core of an AI and the vast, often siloed information and action pathways of the real world. Without such a mechanism, AI remains a closed system, trapped within its training data, unable to adapt, to learn, to act in real time. Consider the profound implications. AI agents gain the ability to access your Google Calendar and Notion documents, thereby evolving into truly personalized AI assistants. They move beyond generic responses to provide contextual and actionable engagement. An application like Claude Code can generate an entire web application directly from a Figma design. This represents a leap from mere code suggestions to genuine creative output integrated with design workflows. And enterprise chatbots connect to multiple databases across an organization, empowering users to analyze complex data sets through natural language interactions. This democratizes data access, transforming raw information into actionable insights for everyone, not just data scientists. AI models can craft 3D designs in Blender and subsequently print them using a 3D printer. This demonstrates the capacity for physical manifestation, bridging the digital realm with tangible creation. And the benefits of MCP ripple across the entire ecosystem. For developers, MCP significantly reduces development time and complexity when building or integrating with AI applications or agents. It provides a standardized blueprint, eliminating the need to re-engineer custom integration solutions for every new tool or data source. For AI applications or agents, MCP grants access to a rich ecosystem of data sources, tools, and applications, profoundly enhancing capabilities and improving the end-user experience. This is how AI moves from theoretical potential to practical utility. For end users, you, the end user, experience more capable AI applications or agents that access your data and undertake necessary actions on your behalf, always with appropriate safeguards. To appreciate MCP's utility further, we must examine its primitives, the elemental building blocks that allow clients and servers to offer each other specific functionalities. These primitives specify the types of contextual information available and the range of actions AI applications can perform. MCP defines three core primitives that servers expose to clients: tools, These are executable functions AI applications can invoke to perform concrete actions. Imagine your AI needing to search for available flights, create a calendar event, or send an email. These tools possess schema-defined interfaces, using JSON schema for validation, and precisely defined inputs and outputs. The LLM, based on the conversational context, decides when and how to invoke these tools. Importantly, tools may necessitate user consent before execution, ensuring human oversight and control over AI actions. Dane's resources. These represent passive data sources that provide contextual information to AI applications. Think of them as read-only information streams, such as file contents, database records, API responses, calendar data, or even previous travel itineraries. Then prompts. These are reusable templates designed to structure interactions with language models. They function as predefined instruction sets, guiding the AI through specific workflows or demonstrating the optimal use of an MCP server. Unlike tools, users control prompts, explicitly invoking them rather than having them triggered automatically. A plan a vacation prompt, for instance, provides a structured input mechanism for destination, duration, budget, and interests, ensuring a consistent workflow. MCP also defines primitives that clients expose to servers, allowing server authors to build richer, more interactive experiences. Sampling. This feature allows servers to request language model completions through the client's AI application. A travel booking server, for example, might ask the client's LLM to analyze these flight options and recommend the best choice. This crucial approach empowers servers to perform AI-dependent tasks without directly integrating with or paying for AI models. The client maintains complete control over user permissions and security measures, and the design often incorporates human-in-the-loop checkpoints for review and modification. Elicitation. Servers can use elicitation to request specific information from users during interactions. This provides a structured, dynamic way for servers to gather necessary data on demand. Imagine a server asking for confirmation of a booking, preferred seat types, or contact numbers to finalize a reservation. Clients display these requests clearly, providing context and validation, and users maintain the option to approve, deny, or modify responses. Logging. Servers utilize this primitive to send log messages to clients for debugging and monitoring purposes. It provides crucial visibility into server operations. Routes. Clients employ routes to define file system boundaries for server operations. These are file URIs pointing to directories where servers are permitted to operate, guiding them to relevant working areas while enforcing security constraints. For example, a travel planning server might gain access to specific directories containing itineraries and templates, but not financial records. Critically, the client always retains full control over actual file access, ensuring that routes communicate intended boundaries, with security policies mediating real access. While integrating AI agents with databases and APIs through MCP. The integration of AI agents with databases and APIs is not merely a technical exercise, it represents a fundamental shift in how we conceive of AI's practical application. This is where AI moves beyond being a sophisticated query engine to becoming an active participant in complex systems. MCP provides the structured, standardized framework to make this integration both powerful and manageable. Ensuring security and control, the ethical imperative. Such powerful integration, of course, necessitates robust security and user control mechanisms. MCP explicitly designs these into its protocol. Explicit approval. Many operations, particularly those involving modifications to local file systems, require explicit user approval before execution. This critical human-in-the-loop safeguard ensures you maintain full control over AI actions. At client-mediated access routes, clients define routes and file system boundaries to guide server operations, ensuring servers only access designated directories. The client always controls file access, mediating it through its security policies. Elicitation transparency. When servers request information via elicitation, clients display these requests with clear context, explaining who is asking, why the information is needed, and how it will be used. Users can provide information via appropriate UI controls, decline or cancel the operation, and clients validate responses against defined schemas. Sampling oversight. Even when servers request LLM completions, sampling, the design allows for human-in-the-loop control. Clients can show what the server intends to analyze, enable users to approve or modify requests, and display the exact prompt and AI response before it returns to the server. Tool control. Applications can empower users to define tool availability, present approval dialogues for individual tool executions, offer permission settings for pre-approving safe operations, and provide activity logs showing all tool executions. This structured, layered approach, with its emphasis on explicit communication, defined interfaces, and integrated security features, provides the necessary framework for AI agents to operate effectively and responsibly in a world of databases and APIs. It is not merely about connecting systems, it is about forging a more coherent, more capable, and ultimately, more useful future for artificial intelligence. We have traversed the fundamental concepts of MCP, its profound utility, and the meticulous process by which it integrates AI with the vital external arteries of databases and APIs. This protocol stands as a testament to the ongoing effort to bring order and functionality to the intricate dance between artificial intelligence and the human-built world. If this discussion has illuminated pathways for you, if it has sparked further inquiry, I encourage you to share your thoughts in the comments below. Your insights and questions contribute significantly to this evolving discourse. Please like this video if you found it valuable, and subscribe to Dr. Carminati's channel for more explorations into the architecture of tomorrow. Thank you for joining me on this journey. Until next time, keep seeking understanding.